Hello everyone, I am Jeevana Gudala. So today I'm going to explain about my project. This is regarding the recurrent neural networks for sequence data, which is nothing but here we explore the time series prediction using the RNNs and the LSTMs. So this is subject regarding the 5560 recurrent neural networks for the sequence data. So in this, we are going to cover mainly the foundational concepts of the RNNs and including how they work and why they suited for sequence modeling. Discuss and we will discuss the data sets which we used for the project, and we'll explore how LSTMs address RNN limitations and demonstrate their real world applications using the stock price data, and will compare the initial and the redesigned LSTM models, emphasizing iterative improvements in performance, and will conclude with the what are the lessons we learned and what are the implications of this work for the in the future applications. So now let's start with the introduction. So here the recurrent neural networks and the long short-term memory networks are essential for the sequence modeling. In this we handle the task like time series forecasting, and this project investigates mainly these models with a focus on predicting the periodic and financial data. The RNNs are a class of neural networks so which specially designed to process sequential data. Unlike traditional feed forwarding neural networks which process the data in isolation, RNNs have a feedback loop that allows them to retain the information from the previous time steps. This feedback mechanism enables us to actually the model the temporal dependencies and the context, making them ideal for the task where we order of the data points are very critical. Here we need to discuss what are the key characteristics of the RNNs. So there are mainly, there are few key characteristics such as the shared weights, hidden state, and the back propagation through time. So here the shared weights, which is nothing but the same set of weights, it's applied across all time steps, which reduces the complexity of the model and ensuring the consistent learning across sequences. And the hidden state, so at this state, RNN compute a new hidden state based on the current input and the previous hidden state. The hidden state acts as a network's memory. The back propagation through time. So this is nothing but a way used to train RNNs by unrolling the network across the time and computing the gradients over all time steps. Here we need to discuss mainly the applications of the RNNs, which we very important. So the mainly which here the applications of RNN are used for the natural language processing and the speech recognition. So in this, it mainly convert the spoken words into the text, which involves the processing sequences of audio frames. And the time series prediction. RNNs are used to predict future values in sequential data, such as the electricity demand, stock prices, or weather conditions. And there are few challenges in RNNs also. So it is very powerful. They are not without limitations. The most significant limitations are vanishing the gradients and exploding the gradients and the short-term memory. The gradients diminish during the back propagation, and it makes very difficult to learn the long-term dependencies. And the gradients grow excessively, leading to the unstable training, which is nothing but exploding gradients. And in short-term memory, RNNs struggle to retain the information over a long sequences. So these challenges have driven the development of advanced architecture like LSTMs, which is nothing but the long short-term memory networks, which incorporate mechanisms to address these limitations effectively. So now let's discuss why the sequential data is important. uh, and a time series data set. So this data, so here we are going here for this project. I have chosen the time series data, which is not the settled weather data. So this data has a range from time data from the January 1st, 2012 to the January 31st, 2015. It mainly has 1460 entries, which is very ideal number for analyzing the time series. So, and it has a key characteristics such as the data set includes the uh, precipitation, maximum and minimum temperatures, and the weather conditions. And the data which we have is in the format of CSV, which can be easily analyzed by using the Python, R, and the Excel. And it has applications such as it is used for analyzing the weather and finding the seasonal patterns, climate forecasting, so hence policy development in urban planning. So and the data quality such as it is used for analyzing the weather and finding the seasonal patterns, climate forecasting, so hence policy development in urban planning. So and the data quality, so here the data is free and it does not have any missing values, which helps to mainly get the accurate analysis. So since the data is clean, so it's reliable for the analysis and it lacks wind speed and humidity pressure information that would further widen the insights. The Seattle weather dataset, it mainly consists of the data from January 2012 to the December 31st, 2015, and it has the main features like the date, so the date which is in the year, month, and the date format, and precipitation, the continuous variable indicating the daily rainfall which is in the terms of inches, and the temperature which is nothing but the maximum and minimum daily temperatures in the Fahrenheit. And the weather description, it's nothing but the categorical value summarizing the conditions such as the like example rain, snow, so in that way. And we have many applications such as it helps to identify the seasonal trends such as rainy seasons and the dry spells. So and it supports the urban planning efforts such as the optimizing drainage systems for the heavy rainfall and the climate studies to detect the long term changes in the temperature and the precipitation. And we have the few limitations also. Since the data set is clear and comprehensive, it lacks the features like the wind speed, so which could provide a more holistic view of weather patterns. So now let's move to the next slide. So now we are going to discuss about the simple RNN with the sine wave data. So this project we are charged with the development of the time series. Here we have used the Seattle time data series. So that uses a simple RNN networks to predict the sine wave data. So it implementation has been done based on the TensorFlow and Keras. So we have used a certain libraries such as the NumPy, so which is used to create the sine wave data, and the pandas, which is used to organize data in data frames, and which are easily manipulated and pre-processed. And we have used the Matplotlib library, so it is used to plot and visualize the sine wave and the model results. And the TensorFlow, so it's used for construction, training, evaluation of the RNN model, for normalizing between the 0 to 1 of input features, time series generated from Keras for creation of the input and output sequences from time series data. So here we have certain objectives for this project, which mainly investigates application of the RNN and the LSTMs in sequence modeling and focusing on the ability to predict the time series data and overcome inherent challenges. So our mainly objective is to implement this simple RNN for the sine wave data. So the sine waves with the predictable and the periodic nature serves as an ideal benchmark for evaluating the foundational capabilities of RNNs. By implementing this simple RNN for sine wave prediction, the project established a baseline for understanding how RNN capture the patterns, and the mainly applying the next objective is to applying the LSTM to the data which I have selected, which is nothing but the Amazon stock price data. So this stock data is very challenging use case for sequence modeling due to its noisy, volatile, and the dependencies. So this project applies LSTM to this task, demonstrating its ability to handle the complexity and provide accurate forecast. And the next objective is to address the limitations of the RNN. So we have certain challenges such as vanishing and exploding radiance, hindering RNN performance. This project mainly explores how LSTMs incorporate advanced mechanisms such as the gating to mitigate these issues and improve the model reliability. And our next objective is to redesign and compare the models. So after implementing this initial LSTM, the network is redefined with enhancements to improve accuracy and efficiency. So by comparing the performance of the initial and the redesigned models, so the model highlights the impact of the iterative improvements and the parameter tuning. So now we are going to discuss about the time series prediction using the recurrent neural networks. So this project is about the prediction of time series using a recurrent neural networks and the data splitting. Here we split the data into 70 and 30%. The 70% we used for the training and 30% is for the testing. And next is the data normalization. So the min max scalar from the scikit-learn will scale the data between the 0 and 1. And the sequence generation using the keras time series generator to generate the input output sequence that feed the RNN. So the model architecture instantiating the simple RNN with a simple layer of 70 neurons, a fully connected dense layer for the final prediction. And compilation on the training, the compilation using the mean square error, which is nothing but MSE. So with the Adam optimizer, the network is trained by calling the fit model on the 6 epochs. The evaluation run the performance on the testing data that were reserved. So here why we use the symbol RNN. So it's nothing but the basic form of the RNN. It consisting of a single recurrent layer. So it provides a straightforward implementation of sequence modeling. So which is ideal for learning the periodicity of sine waves. This experiment is mainly fundamental step and like we call it as a foundational step before progressing to the more advanced architecture like the LSTMs. And next, let's move to the next slide. So here, now let's discuss the results and conclusion of the sign. So actually it does well on the test data set because MSC score was very low. So now the RN is good to make an accurate prediction from the historical data. So this will be usually evident in the comparison plot where the original sine wave are aligned against the RNN predicted values, which is a perfect match between them. So it therefore brings the potential of RNN in doing the time series prediction, especially how the past trends can be generated to make the accurate forecast. And then there we have few limitations also. While simple RNN worked well for the simple task, its shortcoming become evident when scaling to more complex data or longer sequences. So now let's move to a new slide. So now let's discuss about the RNN, the LSTM neural network, the vanishing gradient problem in neural networks. This can be actually realized when the training of the neural network faces problems like the vanishing gradient, the cost function with respect to the weights in its early layers, because it is very small, which is to say close to zero. The gradients during the back propagation through the network will get multiplied times and diminished in size layer by layer. The gradients may completely vanish in early layers, which gives rise to the following sacrifice of the vital information and difficulty in learning the proper representations of input data because of the difficulties in the earlier layers receiving updates, since magnitude of gradients become very small rather quickly. So here we are suggesting the few solutions which include the initializations, giving the weights, good starting values, and activation functions like ReLU, and preserving the magnitudes of gradients and skip connections along with the batch normalizations which help in stabilizing the flow of gradients across the layers. So now let's discuss about the LSTM neural network solutions to the vanishing gradient problem. So here in these slides, we are going to suggest a few solutions for the vanishing gradient problem. So here are the few strategies which can be opted, which is nothing but the activation functions and the weight initializations and improve gradients flow. So in activation functions, which is nothing but the ReLU, which would give the consistent magnitude and gradient and avoid getting the gradients very small. And the weight initialization, in this, the correct weight initialization prevents the weights from being too large or too small, and thus make the training table. And in the improved gradient flow, the batch normalization and skip connections are some of the techniques that stabilize the gradient flow within a network. The efficient weight upgrades with this technique, the gradients will be large enough during the backpropagation to enable the effective weight updates even across deep layers. So this resolution of vanishing the grade problem, which leads to the efficient performance in the neural networks, especially to those layers to better prediction accuracy. Now let's discuss about the neural network exploding gradient problem. So this problem mainly occurs when the gradients of the cost function are too large during the back propagation and hence results in the unstable training in the network. So due to this, it causes some many problems such as a poor network architecture and the high turning rates and the poor weight initialization. So it impacts the gradient values grow efficiently as it moves further down the network, may cause neural network flow. Hence, it results in the divergence or failure to convergence during training. So here we have the few solutions such as a gradient clipping. So these gradient values are clipped to the maximum size to prevent it from exploding. And the weight regularization, this is a method that adds a penalty term to the cost for having large weights. And the weight normalization, this scale updates of weights into a stable range. And the methods such as or the techniques like the weight normalization, gradient trimming, and the use of the various optimization algorithm like RMS prop sequence related the task. So in this we are going to discuss about the LSTM with time series data, build, train, test, retrain, and forecast. So for this we are going to use the Amazon stock price data set. So which has a period of which has a time period from the June 1st to 19 to August 2022 with the sum of 520 entries. It's a time series modeling. So the developed data set was treated as RNN with LSTM architecture because it deals with the time series data involving long-term dependencies and the pre-processing data. Here we are using such as the matplotlib, numpy, and the pandas for the pre-processing of the data. The data in this analysis is fed into the Amazon stock price to pandas and reading parameters of value, open, high, and low prices. So the input data. Here the 158 points of data used as a context to make the predictions of the upcoming one. So here are going to split the data into two parts, which is nothing but the training and the testing data. So the 80% we are going to use for the training data and 20% for the test data. And next we are going to discuss about the next slide. So here in this we are going to discuss about the LSTM with time series data build, train, test and retrain and forecast. So in this the model building the LSTM architecture with the 40 LSTM cells, and here I have highlighted the few main points, and added the dropout layer to avoid overfitting, and the model compilation, the compile model using the mean square error as a loss and the Adam as optimizer, and the model summary showing the sum which shows the summary using the summary parameter. So the total parameters are 50,000 and 851. Now let's discuss about the training neural network model. The training model, so it was fitted using the fit method. The training duration is nothing but the model has been trained for 100 epochs. The loss started at 0.086 at epoch 1 and finally ended at the 0.014 at epoch 100. Optimizer is used. Optimizer in this, the optimizer uses Adam. This minimizes the MSC loss. The loss visualization in this, a plot of loss data from training using a plot function. So now let's discuss about the pre-processing full input dataset and LSTM model fitting for prediction. Normalizing the data. The min-max scaler from the scikit-learn for normalizing the whole input dataset DF, and the common scale. So we need to assume all the data points are in the same range and normalizing the data. In this step, mainly we normalize the data. The normalized data is stored in the variable called as the normalized full data. So the time series generator. So using this generator from Keras, we create a generator to forecast the data, and the time step configuration. In this, the input time series step count is 60. The batch size, if we say the time series generator is 32, and LSTM model fitting for prediction. The forecasting the generator using we are forecasting the generator using all data for prediction. The model architecture. So in this we are defining the LSTM model to be used that contains 40 LSTM cells. The RELO architect activation and the return sequence are true. The dropout layer. In this we are adding a dropout layer to avoid the overfitting. So we are compiling the model using Adam optimizer and mean square error minus MSC loss, so which gives the model compilation. So and we need to fit the model to run the for the 100 epoch. So this helps to optimize the future stock value forecast for the training. So no validation at the early stopping, as the requirement is future projections, there is no role of validation generator or early stopping. So now let's discuss about the LSTM with the time series data build, train, test, refrain forecasting LSTM, which is nothing but the time series forecasting. So pre-processing full input data set. So in the step configuration, if we discuss, the time step count of input series is 60. The so run the time series generator. So in this we take the normalized full data with the same time series length in the generator. So we are using the time series generator, set the batch to the 32 and the LSTM model fitting for the prediction model compilation. So we are defining the model and compiling with the Adam optimizer and the MSC loss. So here we're training the model for 100 airports, optimize the predictions of future stock values and the no validation or early stopping. Since our main purpose is a prediction for the future values, so the validation generator and early stopping are not used. Here we can see in the graph, or you can see the forecast time series analysis in the graph, which is in the slide. So now let's discuss about the results and the conclusion of that. And here we will discuss the um, results and we will compare the test data too. So we'll compare the test data, the actual and the stock price forecasted for the next 60 working days. So here the how well the model predicted. So this graph shows how the prediction aligned with the real stock price trend. And let's come to the conclusion. So the improvement in the model performance, the performance can significantly be improved. So by changing the neural network architecture and training parameters, so if these improvements is done, then it should worth it, since the forecast is of utmost importance in the related fields, be in meteorological or financial. It can be used as an applications and the various experiments were performed to determine the exact number of neurons that the model requires. So here we got the key findings that the redesigned LSTM capture long-term dependencies more effectively and the enhanced architecture and training parameters improved the forecasting accuracy and the robustness. So now let's compare the network performance LSTM models in part 4 and part 5. So let's compare in terms of the architecture, dropout, training, and the performance. So in this, the both models were implemented with the 3 LSTM layers with the 15 neurons. And in the part 5, we optimize the parameters to suit the better model. And in the dropout, both models has employed the dropout. So they both models were employed dropout. So in mainly in the part 4, it had 20% of dropout, which was retained in part 5. And let's discuss about the training performance and we'll compare that. And the part 4 was trained for 100 approach with the batches of 32, whereas the part 5 retained the model using the whole data set on an extended forecasting. So in terms of the performance, the part 5 has low RMSE and MAE, hence considered more accurate on the lines of prediction. The part 4 increased the period for which the forecasting was being done compared to the part 4 and handled the long-term dependencies better. So now let's conclude the analysis. So the neural networks, particularly the LSTMs, excel in sequence modeling and prediction tasks. This project demonstrated how advanced architectures address the limitations of the traditional RNNs. The application of these models, the finance and the climate and beyond, offering transformative potential for solving real world changes. Thank you, everyone.